see how far I want to go tonight. Yeah, this is probably going to be it. I'll just do this last example and then I'll give you the lay of the land and then we'll go from there. So A is an m by n matrix. U and V are vectors in Rn, so n dimensional space. And C is a scalar. Then we have these two properties, all right? So the distributive property. So matrix A can be distributed through vectors U plus V. So the sum of two vectors, visually we learned about what that takes the form of graph, in the form of a graph. Last time, 2 classes ago, I think. And then also we have, it's a form of the commutative property, but basically it's telling us that we can essentially factor out the C scalar. The C can be pulled out or it can be put in to the product. So basically, if it's a constant multiple or a scalar multiple of vector U, I could multiply the two matrices first and then multiply a scalar on later on. So it's essentially the commutative property, but with 3 factors. All right, so the proof here, the first proof, and I'm going to let you try the second one on your own before I spoil that one for you. Neither of them are bad. We have A times U plus V, and we're working in 3 space. So A times U plus V is equal to AU plus AV. Now we're using matrix A as A1, A2, A3. All right, so just simply that. So that's kind of nice. We're not dealing with something that's crazy elaborate. All right. So all I'm going to do is on the left-hand side, I'm going to take matrix A, A1, A2, A3, and multiply that by vector U, which would be U1, U2, U3. I know it would have 3 entries because it's in 3 space, which would then be added to V1, V2, V3. So I'm just working the left-hand side. You could work the right-hand side if you want and make it correspond with the left-hand side. It's up to you. But, I'll just pick a side and start working. Now, we know that vector addition, I'm not talking about the graphical addition, just the act of adding 2 vectors is as simple as adding the corresponding parts. So we're looking at U1 plus V1, U2 plus V2, and U3 plus V3. All right, and so we have the A1, A2, A3 in the front. All right. And I'm going to preface what I'm about to do by saying there's a bunch of different ways to do this, some easier than others. My brain took me in this direction this time. If you look at videos from previous semesters, you might see 4 or 5 different semesters, 4 or 5 different approaches. All right, so there's really no wrong way as long as you're applying appropriate algebraic properties. All right, so by finding the addition here, I just made my life a little easier because matrix multiplication is just telling me to take the corresponding values and multiply them. So simplifying this is really just a matter of taking A1, multiplying it by U1 plus V1, plus, because this is a 1 by 3 and a 3 by 1, so the final result should be a 1 by 1. All right, because we're multiplying here, I'll just make a note of that. This is a 1 by 3, 3 by 1, so the result should be 1 by 1. So that serves two purposes for me anyway. Maybe you don't need to know that, but I like to know that for two reasons. One, to make sure that multiplication is a legitimate move at this point, because I can't make that move unless the number of columns is equal to the number of rows. And then also, it tells me what I should get as a final result. All right? It's just nice to know that.
So you just basically multiply.
Essentially, yeah.
When it's not 3 is the same number.
Yeah, whatever the common value is, you're just ditching it. All right, so then we'd have A2, a couple straight marks there. U2 plus V2. And then A3 times U3 plus V3. Now this isn't a far cry, at least in terms of the mechanics, from the proof behind matrix multiplication to begin with, but there is an element to it where we address the rows and columns and why they are the way they are. So there's that part of the proof that we'll have to address on Thursday. But for now, we can just continue. Distributive property, A1 U1 plus A1 V1 plus A2 U2 plus A2 V2 plus A3 U3 plus A3 V3. Now, in the case of the red line here, the A's were the scalars, essentially, and the U's and V's were vectors. But we could kind of change the role of things and move things around so that all the U's are grouped together and all the and all of the V's are grouped together. So I'm going to write it as A1 U1 plus A2 U2 plus A3 U3. Then for the V's, A1 V1 plus A2 V2 plus A3 V3. All right, so we're actually almost there, because if you see the structure of what we're looking for A multiplied by U and then A multiplied by V. And you say, okay, well, okay, I got A's multiplied by U's and A's multiplied by V's. That's great, but it seems like really all over the place until you realize that this is the result of the matrix multiplication. All right, so the next line is just basically us undoing the multiplication, which is why I was saying you could work the left side of the original equation or the right side, because sometimes if you work the left side and then a little bit on the right, you can meet in the middle and save yourself some work. It's just I got in a groove with the left side, and I was having fun. I like algebra, so sorry. So A1, A2, A3. Multiplied by vector U, which is U1, U2, U3. which ultimately is the same thing as saying AU. And then A1, A2, A3 multiplied by V1, V2, V3, which is ultimately the same thing as A times V. And there's our proof. And again, easier ways, sure. Shortcuts? Yeah, probably. Definitely. Work the right-hand side a little bit, and you could streamline this process, because what'll happen is, if you work the right-hand side, you're going from this to this to this, and then once you get this, you realize it's the same and you're done. All right, so you can kind of get to a point where you're saving yourself a little time, but there's the point behind me showing this stream of consciousness really approach is that there's really no wrong way as long as you're using appropriate algebraic skills, right? And the rules of matrix operations, which you can never lose sight of, because some of them are different enough from ordinary algebra that you'd be like, well, that can't possibly be a thing you could do, and it's totally a thing you could do, all right? So there was a list of properties. I think it was a bunch of pages ago. I can look through and find it at some point, but it said, you know, well, this was one of them, you know, A times U plus A times V equals, you know, and it was a whole list, and it had the identity property and commutative properties and all that. Take a look at those, and anything that looks like it's not common sense, take some time and really think about it and try to think about why that it might be what it is. And also, you know what? Not a bad idea to try to prove it. Because this is the blueprint. You know, you just make up, just be mindful of the space that you're working in. This is 3 space. You could, if you want to dial down the work, dial down the dimensions, all right? Just do the same thing. If you want to do this with a lighter version of this, make it A1, A2, and make it 2 space. The algebra is a little bit easier, and you still get the same, you know, ability to connect the proof to the rule itself, all right? But yeah, these problems are a little bit more algebra intensive. So what I'd like you to do is try this proof for homework, so that again, just like that problem I almost forgot to go over today, you can have an opportunity to experience it first before I spoil it, and then this problem I really like. So let U equal this, V equal that, and W equal that. It could be shown that this relationship is true. I want you to use that fact, but no row operations. And what I mean by that is, if you were to do it by hand, like, I wouldn't want you to put it in reduced row echelon form, which also means don't go putting it into a calculator and putting it in a reduced row echelon form. What you're looking to do is use properties. Maybe one of these 2 properties, to see if you can establish that this is a true relationship based on this information. All right, we'll see if the properties can get us there and save us from having to do row reduction techniques. All right, so that's where we're going to leave it for tonight. So we want to prove A times C times U is equal to C times A times U, using A times C times U as a linear combination of the columns of A. All right. So linear combinations is really just talking about the sum of the product. All right. So the good news is, well, I guess it's a variety of instances of good news. We already kind of did the hard work, because in the first proof, we figured out what A times U is. All right. It was just kind of buried in the work. But really, it's just a matter of, if you were to take this row, because we're still in R3, take this row and multiply by just the U1, U2, U3, you would have gotten what we need for the left-hand side, right? I'm sorry, the right-hand side. So, but what they want us to do here is using A times C U as a linear combination of columns of A. So it's really just telling us stay on the left, at least work that a little bit and see where it gets you. All right, so that's what I'm gonna do, and just desperately hope that there won't be a lag with my new device. All right, so U we're defining again as U1, 2, and 3, which would mean that CU is C times that, which is going to be CU1, CU2, and CU3. All right, because it's a scalar multiple. All right, that's just kind of itemizing everything that's happening on the left-hand side. All right, so then we're going to take A, so I'll just note it here. A again is the first row of matrix A, A1, A2, A3, because the reality is we could prove everything we need to prove with just one row, because if we were to do this with like a 5x5 matrix, we'd be here like for the rest of the semester trying to figure this out. So a lot of moving parts. So what I'm going to do now is find the product of A and CU. A little too close there, I think. So that's going to be the first row of A. U1, CU1, CU2, and CU3. All right. The product of the row and the column, that gives you the form of a linear combination. All right. Because we're multiplying the corresponding parts. So I'm going to take the A1 and multiply it by CU1. All right. So as a result, I mean, it's commutative, so I can put it in any order. I'm going to write it as A1 CU1, and then A2 multiplied by CU2, and then the last one would be A3 CU3.
How do we know that there are three elements of A within A?
Oh, because we define this as an R3 system, and in order for A to correspond and allow for multiplication, the number of elements in A has to correspond with the number of elements in the vector. All right, so it's an assumption that has to be made, but it's a correct assumption based on the fact that multiplication can't happen unless the number of columns here is corresponding to the number of rows here. That's a good question. All right, so we're going to take the sum of these values. And that's really the form of a linear combination. All right, a scalar, the C, multiplied by something, really, I mean, involving a vector, and repeatedly, and then all those values added together. All right, so CU we're defining as the weights imposed upon matrix A. All right, so it's just a question of, does this correspond to what the question is really asking for in terms of a final answer? All right, so again, prove that ACU is the same as CAU. All right, so slight adjustment to make that happen. CAU is what I'm looking for, so I'm just going to reorganize a little bit. CA1U1 plus CA2U2 plus CA3U3. All right, a scalar multiple can be factored out completely. So I can factor it out of the whole shebang if I wanted to. Based on what I'm looking for on the right-hand side, it seems that I do want to do that. O&C is a coefficient. So that's going to be my next step. So C times A1U1 plus A2U2 plus A3U3. All right, so A and U are represented in the linear combination form, but still I want it to be represented as a product of A and U. All right, so we would just want to think, well, what was this prior to becoming this expanded form? What it was is kind of how we handled it before. I'll just kind of scroll up and show you. It was in this form before it was distributed out, multiplied out and distributed, simplified, reorganized, and all that stuff. So why would it be any different going the other way? And so we actually did that part of it 2 days ago. A1U1, A2U2, A3U3 corresponds to this relationship. So it's really just a matter of reproducing that. So I have the C. I'm going to go blue for those keeping score at home. And then that's going to be multiplied by A1, 2, and 3, which in turn is multiplied against U1, 2, and 3. A1, 2, and 3 is the same as matrix A. U1, U2, U3 is the same as vector U. And the C is all by itself out in front, C times AU, which ultimately is what we were looking for. Let me just draw a little line to make sure that nobody confuses these two things for being part of the same solution. So, you know, I can go with analogies, I can go with idioms and cliches and everything, like it's always darkest before the dawn, and round the rugged rock, the ragged rascal ran. I don't know, it's just whatever pops in my mind. Bottom line is, like when you do this stuff, you gotta expand it out, you gotta get a little dirty here before you can start cleaning it up and seeing what's going on, all right? So, carry out the operation on the left-hand side, expand it out all the way, and then once it's in fully expanded form, take note on the right-hand side of what you're looking for, and then start the process of reorganizing. All right. So the second example here, let U equal 725, V equal 313, and W equal 511. It says it can be shown that 2U minus 3V minus W equals 0. Use this fact and note row operations. Well, to find x1, y1 and that satisfy the defined. There's so much wrong with the structure of this in terms of like grammar. It looks like I have a closed paren here, but no open paren, so that doesn't need to be there. Or maybe a corresponding open paren. Use this fact and note row operations to find x1 and y1 that satisfy the equation. That's just awkward. To find the values x1 and x2 that satisfy the equation. All right, so that would be two distinct typos if anybody's in need of typo bonus credit. So the grammar for this part, and that's one of them, and getting rid of the closed paren, that would be the other one. All right, so at your leisure, if you submit that, you will get your bonus points. Some folks are already maxed out, so that's good news. If you're wondering if you got bonus credit again, just take a look on Blackboard. If you submit an error on Remind, just take a look sometime like the afternoon or the next day. If you didn't get the bonus credit, I mean, there's a slight chance I didn't get around to it, but very unlikely. It usually means that somebody just beat you to it. All right. So first thing I'm going to do is take a look at the 2u minus 3v, etc. So, but I don't want to box myself out here. I need to actually see the u. So 2,725 minus 3,313 minus, I'm going to put a 1 in there because it's minus w, but I like to have a constant multiple there, or a scalar multiple. 511 equals 0. Let me clean that up. That one got a little out of hand here. All right. So scalar multiples tell me that I can actually just multiply a vector by that value. So I'll have 14, 4, and 10. I'm going to bring the entire scalar and use that as my multiplier. So I'll have a plus. I mean, that's a preference kind of thing. I mean, you could leave the minus, but then you'll have a minus. Right? One way or the other, you're going to have a minus. So it's like, it is what it is. But I like to have a little consistency in my setups. Just a little bit. I don't want to go too crazy with consistency, though, because then people start expecting too much out of me. All right. So I'm really just at a point where I'm going to verify that this is going to be a true statement. All right. So if I combine terms, I'd have 14 plus negative 9 plus negative 5 equals 0. And you can do the same thing for each of them. What's that? It's going to be all 0, exactly. So then we get to a point where we look at, so we have verified that it's all going to be 0, so we're good there. We want to make sure that, because, it can be shown that. All right, I'm not going to take anybody's word for that. I'm going to verify it myself. All right, so what I'm looking for is an x value that would satisfy this equation. Well, if you know how to multiply matrices, and again, no row operations, if you know how to multiply matrices, then that's one skill. I mean, really, it's the only skill that we have other than row reduction at this point, at that and plugging stuff in the calculator. And again, that's, I think I mentioned this last time. If you plug it into the calculator and hit RREF, you're doing row reduction, right? Just because you're not showing the work, you're still using that technique. So that's cheating. Like, not cheating as in like academic integrity cheating, cheating as in like defying the spirit of the problem, all right? So what we're going to do here, we want to play by the rules, the math rules. So first row by the column vector is going to give me 7x1 plus 3x2. All right. Now, I'm going to off on the side here, I'm going to just make a little note that I'm looking at a 3 by 2 vector against, and that's going to get multiplied. I'll use a different multiplication symbol because that gets a little crazy. Multiplied against a 2 by 1 vector. 3 by 2 matrix against a 2 by 1 vector. I think I said vector for the matrix, but maybe I didn't. I don't know. So I'm looking at a 3 by 1 result. All right. So then
I would take the 2, 1 and multiply 2x1 plus x2. And then I would take the 5, 3, 5x1 plus 3x2. All right. So I should get a 5. I should get a, red. I should get a 1. And I should get a 1. All right. All right, so we have 3 equations with 2 variables. So there's a couple of ways you can go about this. Now, you have a choice, because they gave you this fact, but then you might look at it and say, well, I don't know that that fact is absolutely necessary. All right, because I have 3 equations with 2 variables. Algebraically, it's not terrible to solve this out just by hand. All right, so you might consider something like elimination or something along those lines. All right, so let me show you that way first, and then after that we'll see about incorporating the other information. All right, so I would look at just maybe the first. I think it makes the most sense to go with the first equation and the last equation. And subtract from it the last equation. I put a 2, I meant a 1. So we'd have 2x1 by subtraction equals 4, making x1 equal to 2. All right. Now, we're kind of on to something, and I'll explain what I mean by that in a second. But let's find the other value. So 7. Let me take an easier one. I'll go with the red one there. I think that's the easiest one. 2x1 plus x2 equals 1. So 2 times 2 plus x2 equals 1. And so we get x2 is going to be equal to a -3. All right. If you're noticing some familiarity here, that's probably a good thing. All right. And that's because that information is directly coming from the coefficients of your linear combination. So undo, bless you. So what we get from this, I didn't do any row operations. I kind of wiggled my way around that. I did some algebraic work. But what we get from the justification, and honestly, even if you did the row operations just to get a sense of what's going on, what you would come up with would be some really useful information. Bottom line is, when they give you this linear combination, the -3 and the -1, they're telling you the coefficients of x1, y1, and then they're also giving you information related to a free variable. All right, but as it turns out, just by verifying this, we determine the legitimacy of the 2 and the -3 as the values for x1, x2. Now, if there were a third one, so if we had a third column and an x3 here, then that third coefficient would have become relevant. As it turned out, in this case, it wasn't. But what this tells us is that if you already know the linear combination, then none of this work would be necessary, but we had to do it the one time to at least make sure that it's legit. All right? Bottom line is, whether you're doing algebra or row operations, what you're getting by solving is the scalars acting upon the vectors to give you the vector in question. All right? So you have you can call them the component vectors that make up whatever the true vector is that you're looking for. these values, the 2, the -3, and the -1, are the scalars acting upon those. All right. So thinking back to all those row reduction problems that we did, when we're finding span, when we're setting up the C1 V1, C2 V2, and all that, it became a process. It's like, okay, put it in matrix form and row reduce it. What do you get? Well, you get C1, C2, C3, but if you're not really thinking about what it's giving you and why that's important, then you never really gain anything from it, right? So this question was designed for you to say, oh, so if they give you that kind of relationship, they're really already telling you what the scalars are. So I wouldn't have to do any work, all right? So that kind of a question on a test would be more like a gift than anything else, you know, because if I tell you U, V, and W, and then I give you the resulting vector, then that would be the end of it. Because if I give you that linear combination, the work is already done. You just have to recognize that. Otherwise, you're spinning your wheels and wasting your time. Question?
Yeah, I get confusing in the last 2 steps.
Over here?
Yeah.
I just took the first and third equation and subtracted the third from the first. So that canceled out the 3 x2s, gave me a 2x1 and a 4, and then I just divided. So that gave me solution x1, and then that's when I knew we were on to something, because that 2 corresponded with that 2. And then I just used that x1 value in what I deemed to be the more convenient of the 3 equations. You could have put it in any of the 3. I just liked this one better because the numbers were simpler. Right? All right, so then the big question would be, all right, well, what would happen, you know, you think about the whole linear combination thing and you say, wait a minute, isn't it supposed to be equal to something, right? Normally we would say x1 times u1, x1 times u plus x2 times v equals w, all right? Now, if you think about it in that context, what we would be looking at is the linear combination. And this is kind of the lead into the next lesson. The linear combination is usually written in this form. All right, where you're applying a scalar to a vector and another scalar to another vector, and then putting it all together to get the third vector. Or maybe 3 vectors together to get a 4th vector, or whatever. But by setting it equal to not 0, but the 0 vector, you know, we write 0, but if everything else is in 3 dimensions, then it's 0, 0, 0, not just the number 0. But we write that so that if we're in 10 dimensions, we don't have to create one vector that's got 10 zeros in it. That's a waste, all right? But just by simple algebra, if I subtract the w from both sides, I get this linear combination, which allows it to be set equal to the 0 vector, all right? And so what we end up with is, like I said, it's a lead into the next lesson. That's going to be what we call a homogeneous matrix equation. Right on cue. It's funny how that works. So homogeneous linear system is what we make matrix equations out of it. So we've already talked about the parametric form of the solution to a linear system. So I think we can kind of like jump into examples, and what I'll do is just to not ignore the concept, because I know if you're, I always hated that when I was a student. It's like, well, we've already talked about that, so you know that like the back of your hand, so we're just going to move on. And you're like, oh, what if some of us don't know it like the back of our hand? Could you possibly review that? Yeah, so when we get into the actual solution, I'll point out what part of that solution represents the parametric vector form, all right? But basically, if you look at the structure of it, it sure looks an awful lot like a linear combination, right? So you have a scalar and a vector, another scalar, and another vector. Each multiplied, and then the results added together, all right? So the same structure. Doesn't necessarily have to be the same variables in the same order, but it's the same general structure. So a homogeneous system is one in which all the numbers on the right-hand side are equal to 0. Okay, that's an oversimplification. but I mean, it's a good working one because if you look at this matrix right here, you see, last column, all zeros. All right, so easy to identify visually. But what that means is that the equation was solved so that 0 is on the right-hand side. All right, so just like what I was talking about on the previous page, you might have 2x plus 3y equals 4, but I could easily move that 4 over to the other side and make it equal to 0. All right, that's all that's happening. All right, so homogeneous system is always going to be in the form of ax equals 0. All right, and one of the solutions is always going to be what we call the trivial solution. All right, so that's kind of it's kind of weird because you're like, what does that mean? Because we're going to have trivial solutions and then non-trivial solutions, and then I'll make a comment like, oh, that one's just the trivial solution, and you'll be like, oh, okay, thanks for putting me in my place. Is that your way of saying that that was a stupid answer? Like, well, that's very trivial of you. No, it's just saying that if I'm going to take two values and multiply them, one instance in which the result could be 0 is when you're multiplying by the 0 vector. All right, so if I were to say I have matrix A multiplied by vector x with components x1, x2, x3, and I say what's x1, x2, x3, you might say x1 equals 0, x2 equals 0, and x3 equals 0. And I would say that's the trivial solution because that's the one that would work no matter what. So then I would say, okay, what about a situation where x is some non-zero vector, but also gives a result of 0 through multiplication? All right, that's the non-trivial case. Because we know we can always get to a 0 if x is 0. But can x be something other than 0 and still give us a result of 0? All right, that's the important thing. Because in ordinary algebra, you have two factors. When you multiply those two factors, can't get a result of 0 unless one of them is a 0. There's no way to do it. But in linear algebra, through matrix operations, you can get a result of 0 even if the two matrices are not themselves equal to 0. All right? So very strange stuff, but that allows for, well, honestly, the topic doesn't exist without that relationship. So it allows for this lesson to exist. So, look at that. I'm just giving away typos today. Yeah, you know what? There was an example 1 at some point. It was probably a stupid example. And I said, let me get rid of that. So I got rid of it. But then never renumbered my remaining examples. So we got 2 typos here. I'll take them as 2 separate ones. All right. So, example 2. Solve ax equals 0 if A is defined as this matrix, but we do understand that if we have a 0 column, ignoring that 0 column, we can do the same things, row operations on everything except for that 0 column, because no matter what we do in terms of row operations, there will be no impact on that last column. All right, I can multiply, add, I can swap, I can do a scalar multiple. No matter what I do, this column is always going to remain as 0. So why do I even need to write it? So I can ignore it completely, but then I have to remember that it's still part of the equation later on. I always worry about that I'm going to forget. So what I do typically is I write the zeros on the outside, right, indicating that I don't need these values in order to perform my operations, but they're still there. All right. So let's tackle this one, and really, honestly, there's not much to tackle because it's already in reduced row echelon form. All right. So we just have to write up the solution, and that's where the discussion of parametrics is going to come into play. So we know again that we're looking at matrix A multiplied by x equals 0. Matrix A, so again, matrix then vector. All right, terminology, notation, everything's really important because people who sit for this test, they don't familiarize themselves with that. They just can't get past the fact that that just looks like an algebraic expression. And I have had people when I asked them to solve ax equals 0, I have had people say x equals 0 because divide both sides by a, 0 divided by a is equal to 0. They ignored all the matrices and just did the algebra on that expression. And my response to that would be, well, why did I even bother with the instruction? Because if you could do that in every case, then why do we need matrices? All right. So what I want to do is take note of really what's going on here, because after multiplying a by x, I came up with this matrix. Now the last one again is equal to 0, but I do want to think about how this could have ended up being the case. All right. So I have a 3 by 4 matrix as a result of the product of a and x. All right. So I do have to think about that, but I guess that may be like overcomplicating it for now. So I'll take you from the ax to the matrix later on. For now, we'll just worry about the solution. So as it was before, we know that the first pivot value is going to, well, assuming it's in the upper left-hand corner, it's going to be associated with x1. All right, so let me focus on that for now, the parametric form. So I'm looking at x1 plus 0x2 plus 0x3 plus 2x4 equals 0. All right. You don't have to write that out in every case. I just want to do it this one time. And my reasoning for that is to really justify that, okay, so mission accomplished. I know I'm dealing with a 4-unit vector. All right. So my vector x, so I'm just going to put it off on the side here. X is equal to x1, 2, 3, and 4. All right, that's a 4 by 1 matrix. Four rows and 1 column. All right, now again, ignoring the 0, I ended up with a 3 by 4. All right, so through the product, that had to play out somehow. All right, so we'll get to that in a sec. So the next one is 0x1 plus 1x2 and so on. Also equal to 0. And the last one is 0x1 plus 0x2 plus 1x3 plus 1x4 also equal to 0. All right, so I'm just going to go through and circle in the first one anyway the two relevant values. And you could see here that I can define my equation, my solution to the equation, x1 in terms of x4. Just by subtracting from both sides, so negative 2x4. I could do the same thing with x2, also defining it in terms of x4. I missed the positive sign there. And then the same idea for the last one. x3 defined in terms of x4, so negative 1x4. All right, so you see in each case, I'm looking at a variable being dependent upon x4. All right, so bless you. So we know x4 is free. And again, that's the same as saying x4 is equal to x4. All right. By noting that it was a 4x1 and that it was x1, 2, 3, and 4, as indicated by all of these variables, even if the coefficient zeroed out, I know that I'm looking for a 4-unit vector solution. All right. So when I write up this solution, I could write it in a couple of ways. One way would be to say that x sub 1, 2, 3, 4 in vector form would be equal to x4 multiplied by -2, -2, -1, and 1. All right, so that's one way to write it. Or coefficient of 1 in front of the x4. Another way to write it would be to say, well, x1, 2, 3, and 4 is the same as just x. Regardless of how many dimensions there are, it's still just x. So I could say x equals x sub 4 multiplied by -2, -2, -1, and 1. But honestly, I think it's so very important that you take note of what these values are, because otherwise, I mean, I have had, I can't even count the number of people who put, the number of people who have indicated that it was x4 times -2, -2, -1, leaving off the 1 because they just didn't take note of this, and then when they went to list out their solutions, all they got is x1, x2, x3 equals. They didn't even consider that x4 would have to be equal to something too. It's also a variable. All right. So that there's that way of denoting it. And then finally, the last way to represent it well, there's really 4 ways to represent it, but this, like the last 2 ways are really the same way, just written slightly differently. So I could write x1, x2, x3, x4 is equal to 0 plus x4 times all that other stuff. And like I said, the streamlined version of that would be just the same as saying x equals 0 plus x sub 4 times -2, -2, -1, 1. Okay, so you might look at it and say, well, what on earth is the purpose of having the 0 vector included there? Really, it's that at this point, it's more of like a placeholder. It's indicating for us that, you know what, there's not always going to be just a 0 vector. Sometimes it could be some non-zero vector, like 1, 2, 3, 8, or something like that, plus the free variable multiplied by the vector. All right? So you would have a general solution, and then you would have a particular solution. Kind of like if you're thinking in terms of differential equations. And there is, surprisingly, a tie-in between this course, later in the course, and differential equations. So this is the particular solution. And this is the general solution. All right. Now, when you're dealing with non-homogeneous, I almost said differential equation. When you're dealing with non-homogeneous linear systems, these, it will have the same structure, but these will have different names associated with its breakdown. But the structure itself is going to be the same, regardless of what it's called. It's still going to have the same general structure. You're going to have something in particular where it's not related to a free variable, and then you'll have something where there is a free variable associated with it. Okay. All right, so then you might consider, all right, through the multiplication process, how could you have come up with this 3x4 matrix to begin with? Well, the only way that it would have worked, it would be if you were multiplying this by a 1x3 matrix in order to actually carry out that multiplication. So you'd be looking at actually, no, forget what I was about to say. They gave us the A. So I was about to talk about how you'd figure out what A was given a product, which is a subject in and of itself, but I forgot they actually gave us the A, so it's irrelevant. Forget what I was going to say.
It says we usually ask us to have a particular solution and a general solution, or we would ask for one.
I could ask you to put it in any particular form, and then also I could be referencing those forms as part of a question. So like, given a matrix equation AX equals B, for example, which is what we're going to get to in a few minutes, knowing that a particular solution is this, tell me what the general solution would be, you know? So something along those lines. So you do need to know the structure of it and also the names associated with that structure. All right, so these other problems, they're all in reduced row echelon form, so it's really going to take on the same structure. All right, so I didn't really feel the need to go too nuts with this because the reality, and that was the example one that I deleted. It was an example where we went through the row reduction process to get it in row reduced form to then do all this stuff. And it was like, the real problem has nothing to do with row reduction. It has to do with everything with the actual solution once you have it in row reduced form.
But what do you do when the first pivot isn't referring to the x1 value?
When the first pivot, like in this particular
We're
case?
starting right off with the system of equations that's only defining x2 and x4.
So you're gonna have two free variables.
Two free steps.
Yeah. So that one's gonna be a little juicier, but still very manageable.
And there's the free variables are set equal to themselves, not necessarily set equal to each other because they are separate free variables, not in linear.
Exactamundo. All right, so 5, I don't need that. What is that all about? So 5 and 6 are the same idea. So again, it's just practice in writing the solution. So I'm going to put stars on those so you can play around with that. And the bottom line, you're like, oh, you didn't show us the hard stuff. It's going to come up in the non-homogeneous. So that's why I feel like it would be a little bit of a waste of time to go through all of these right now. I'd rather you try those on your own. All right. But the non-homogeneous system is really just dealing with a case where the right-hand side is not equal to 0. Right? So it's like, okay, well, what do we do there? Well, there's a couple of things that we could do. One would be to actually write it so that it's equal to 0. Solution to a non-homogeneous linear system. If AX equals B is consistent for some given B, and P is a solution to the solution set of AX equals B, then the solution set of AX equals B is the set of all vectors in the form of W equals P plus VH, where VH is any solution of the homogeneous equation AX equals 0. All right, so AX equals B, we're saying it's a consistent system for some given B, and we're calling P a solution. Then the solution set of AX equals B is a solution set of all vectors in this form, so our answer is going to be the same structure, the sum of two vectors, possibly involving a free, but one of which is going to be the solution of a homogeneous system, AX equals 0. So that's our first step. So our first step in the process, again, solve AX equals 0. So really, in this case, FX equals 0. So what I'm going to do is take that matrix and get it into row reduced form. Let me see if I can get this to work for a change. Edit. A. Oh wait, no, this actually worked. Shocking. All right, so I get my matrix in. I could leave the zeros off or I could put them in. It really doesn't matter because the calculator is doing my my calculations. I just need to remember that there's going to be 0, 0, 0 on the outside. So reduced row echelon form of matrix A is going to be that. All right, so 1, 0, negative 1. 0, 1, negative 1, and 0, 0, 0. All right, so this is my RF. So just thinking forward to the test, the only time that you're actually doing the row reduction stuff by hand is the instances where I tell you to. All right, every other time, if I say determine span or solve the linear system, blah, 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 whatever the instructions are, if it doesn't say to use the row reduction techniques that we learned in class, you do not need to do it by hand. Calculator is the way to go. All right, otherwise you'd spend the rest of your life on some of these problems. All right, and still not even get it right.
Would that usually be the case? Like we could just do it by calculator instead of by hand, like the row reduction technique?
Yeah, but there's going to be I was going to say exactly 2 instances on the test where you have to do something by hand. There's one definitely where you got to take it beginning to end, and it's pretty beefy. So, you know, like you're not off the hook. I mean, that's really what it's coming down to. And unfortunately, that's probably not what you wanted to hear. Just checking something here. I'm just making sure I'm not lying, because I really don't want to lie about stuff like this, because I feel like lying is a bad thing to do. It's just, you know, it's not where I want to be, you know. Of course, it would help if I looked at the right file. Damn it. Because I was looking at the final exam, and that doesn't help us right now. outrageous. Well, the last time I gave a test, there was like 3 or 4 instances where you had to do stuff by hand. There's no way. Like, I don't want to do that this time. I'll commit to 2 instances where you'll have to do it out by hand. I'm not promising that they're going to be easy, but I'll keep it at 2, because otherwise it's kind of overkill. I learn from my mistakes sometimes. So anyway, we have x1 minus x3 equals 0. x2 minus x3 is equal to 0. And then x3 would be equal to x3. All right. Now, any of those 4 forms that I talked about on that previous page are fine. More than fine. Completely and totally acceptable, perfectly correct. All right? I don't want to make it seem like one's better than the other. All right? So, but the one step that needs to happen would be, and you don't have to show it to me, but you do have to at least take note of it. x1 is equal to x3. x2 is equal to x3. And x3 is equal to x3. All right? Which is the same as saying that x is equal to x3 times 1, 1, 1. Vector 1, 1, 1. All right? So x as in x 1, 2, 3, but just writing the x, it's implied. Because honestly, I think it's pretty clear that vector x has to be x 1, 2, 3, because you wrote it a bunch of times already. Right? So what we did here was we violated the terms of the problem. We just did what we wanted to do. Said, okay, I know you have fx equals b, but we're going to do fx equals 0. Forget your problem. I'm going to do it my way. All right? So obviously this is not the correct and final answer. So we got to do something else. All right? And that something else would be actually solving fx equals g. All right? So that's going to be the matrix in the form of 1, 2, -3, 5. So this is not homogeneous. 2, 1, -3, 13. And then -1, 1, 0, -8. So this one is fx equals g. All right. So what we're going to do is go back to our calculator and ref this bad boy. Wrong one. Second matrix. Edit. A. This one is now a 3 by 4. And you'll see how it extends to give you one more column. Everything else is going to remain the same. I'm just going to chuck the 5, 13, and -8 in there. I said -8, but I did not hit enter. There we go. Then I'll quit out, because my previous operation should be sufficient to get me that row reduced form. So we're looking at 1, 0, -1, 7, 0, 1, -1, -1, 0, 0, 0, 0. All right, now, of course, as always, that's assuming that I typed it incorrectly. It's part of the fun, I guess. Verify. Looks good. All right. something to be mindful of here. We're looking at, this is not a zero vector anymore, just like, over here it was. So when we're actually cleaning this up to get it into the appropriate parametric form, this part is the right-hand side. So if it helps, draw yourself a little barrier to remind yourself that it's the coefficient vector, coefficient matrix, the 3 by 3, and then the solution vector together that give you the augmented matrix. So x1 minus x3 equals 7. x2 minus x3 is equal to -1, and also x3 is equal to x3. All right, little housekeeping. x1 is equal to 7 plus x3. x2 is equal to -1 plus x3. x3 would be equal to 0 plus x3, which is telling me that x is equal to 7, -1, 0, plus x3 times the vector 1, 1, 1. And so that first part of the process is really just to demonstrate to you that part of the solution to the AX equals B actually is the homogeneous solution. And that was given in the rule above, but it wasn't clear. I mean, it was in linear algebra textbook form. If AX equals B is consistent for some given B and P is a solution, then the solution set of AX equals B is a set of all vectors of the form of W equals P plus V sub H, where V sub H is any solution of the homogeneous equation AX equals B. Now, when I say it real fast like that, it sounds like much more intelligent and difficult and all that stuff. But really, all that's saying is embedded in your AX equals B, or in this case, FX equals G, is the solution to the associated homogeneous linear system, right? You see you have the x3 times 1, 1, 1. It's here, it's here. So one part of it is going to be the particular solution, just like it was. The P part of the equation. And then this part here takes, like I said, it takes on a different form. It's the solution to the homogeneous system. And we call V sub F. Well, V sub F. Jeez. You know, you've been teaching too many courses in too compressed of a period of time when you start putting velocity final instead of homogeneous vector. Ay, ay, ay. And then a homogeneous differential equation instead of homogeneous linear system is like linear system, linear differential equations. It's like it's designed for you to get those two courses confused. Right? So, I guess it would be even worse if you were a student taking those two courses at the same time. That would be pretty rough. All right. So, bottom line is, what do we do here? Reduce row echelon form. So, like I was saying last time, if you're ever in doubt, put the matrix in your calculator and RF it. It's just a question of what is the interpretation of that, you know? And in reality, the interpretation isn't overly difficult. It's just a question of getting the terminology right. It's always going to be coming down to the terminology. All right. And also, I think I wasn't lying when I said that by solving this problem, we were really reinforcing those problems that I skipped, that I put the stars on, because part of this was, again, going through a homogeneous system. All right. Kev, you got a question?
Yeah, I was just gonna say, what's the difference between, because I'm so confused about the homogeneous and the particular solution.
So homogeneous system is 0 on the right-hand side. And so when you're looking at the solution where 0 is not the only thing on the right-hand side, part of that result is going to be the solution to the homogeneous system. So if I had fx equals, well, in this case, the g vector, to go through this process, as part of the solution, I'm getting the homogeneous solution, all right? Then when you put that together with the particular solution related to this resulting vector, put it together, that gives you the entire solution for this linear system. All right.
So the fx equals 0 was just a part of
Yeah,
that.
it's kind of the lead up to this. Because really, if you think about it, the general part of it, that's why in the previous page I called it a general solution, because you have fx equals 0, that allows for the vector on the right-hand side to have a basis of the 0 vector, which is where everything starts. So I know that if I have a solution for a linear system that incorporates 0, I know that since every vector has to start at 0, I know that that's going to springboard out into every other possible solution, because every solution has to start at the 0 vector, otherwise it's not a vector.
Is there a reason for the general solution that you made the free variable one? Or is it
Is there,
like a particular reason that you've made the free variable one equal 1?
the free variable is, it just has a coefficient of 1, only because if I'm just looking at coefficients of the variables, once I say that x3 is equal to x3, x3 is, it's the same as x3 is equal to 1 times x3. So since we need a coefficient for each variable on the right-hand side, the natural coefficient would be 1. And the moment you've all been waiting for. Word problems. It's nothing. It's mere child's play. Yeah, it's really just intimidating to look at, but really, okay, I'll just kind of spoil it. Once you come up with your equations, you're going to put it in matrix form, and then you're going to row reduce by typing it into your calculator and hitting rrep. So, same idea. When in doubt, put it in reduced row echelon form, all right? And then from that, you'll get the actual value. So, what's the difference between this and all the other problems that we were doing? Okay, well, instead of x1, x2, x3, we have p, m, and g. That's the only difference, right? And a little bit of context associated with it. So, actually, the benefit of a problem like this is that you have a fighting chance of being able to interpret your answer. All right, but the solution of this is what some call a vectorless solution, and so what that means is that, you know, if you were to actually graph the solution, you know, you could write it in vector form. I mean, I suppose you could write anything in vector form, but if you were to graph it, write it in vector form and then graph it, that diagram wouldn't really have a whole lot of meaning, right? Because what does a vector related to 5 sheets of craft paper, 2 boxes of markers, and 3 glue sticks really mean? You know, I don't know what the craft paper axis, the box of marker axis, and the glue sticks axis would have to do with 3-dimensional space. All right. So you could visualize it in the form of a graph, but that graph is not going to have a whole heck of a lot of meaning. All right. So we have Jesse, Maria, Charles went to the local craft store to purchase supplies for making decorations for the upcoming dance at the high school. And of course, they were thinking matrices and, you know, linear algebra when coming up with all this stuff. Jesse purchased 3 sheets of craft paper, 4 boxes of markers, and 5 glue sticks. All right. So right back to algebra 1 here. 3 sheets of craft paper, which is P, 4 boxes of markers, and 5 glue sticks. All right. And then, of course, you know, just because no worksheet would be complete without a typo. Just like I like to make sure I have at least a good, juicy typo on every page of my packets. P does not actually represent the number of sheets of craft paper because they've already told us that. We need the unit price, the cost. The unit cost. I really need somebody to submit this typo for me because I'm pretty sure that I've had to make this adjustment every semester for the last at least 10 years. So, bill before taxes was $24.40. Maria spent $30.40, so I'll just put that over here. When she bought 6P, 5M, and 2G. And Charles spent $13.40, bought 3P, 2M, and 1G. All right. Now, personally, when I'm dealing with a word problem like this, because you know it becomes a little too rote, a little too mechanical. When you honestly, this whole course becomes a little rote and a little mechanical. It's kind of not fair because you, on your end, you develop good habits, and those habits are related to the procedures. But sometimes it's very easy to lose sight of like what it is you're trying to work through. And so I know that you could take the coefficients and put them all in a matrix, row reduce it, and you'll know what the P is, the M, and the G are. But structurally, I think you need some kind of transition in order to get there, all right? And that transition would be 3, let me actually do it in a completely different color. 3, 4, 5. 6, 5, 2, 3, 2, 1, multiplied by PMG. And you know, you can verify through the multiplication process. If I take this row, multiply it by that column, 3 would get multiplied by P, 4 by the M, 5 by the G, all added together. That would give us this. It should result in the total cost vector. That sounds fancy, total cost vector. All I did was I took the name for what it was, like in common sense terms, and then threw the word vector on at the end. Alright. Be like, go over to Captain Lawrence and you look at the menu, because they always have like the different types of beers, the cost, and then they have my favorite piece of information, the IBUs. I can create an IBU vector. International bitterness units or something like that. But basically it's like how bitter the beer is. Now if they had that for everything, that'd be great. Imagine going into like the produce section in the supermarket. You're like, I like fruit, you know, but I don't want it to be too tart. So they give you the IBUs on each one of them, and you're like, oh, okay, this is perfect. I like the low IBUs and nice healthy fruit, and it's not going to be too tart. you know, so you can do that for everything. Have it for like teachers' personalities. IBUs. Oh, your IBUs are really off the chart. You must be like a real nasty person. So anyway, those would all be represented in vectors because they're common variables, or the common units allow for them to be grouped together. All right. But then ultimately, what are you doing? You're taking all this, putting it in your calculator, and hitting ref. All right. So 3, 4, 5, then 24.4, 6, 5, 2, then 30.4, 3, 2, 1, and then 13.4. All right, so matrix, reloaded. So 3 by 4, which is what I want. So 3, 4, 5, 24.4, 6, 5, 2. And I don't want anybody to think, you know, like my reference to Captain Lawrence, you know, it is a beer reference in math class. It might sound inappropriate, but like, it's totally okay. I mean, I support all of the different places, not just Captain Lawrence, like Yonkers Brewery, also a good place. Brooklyn, there's Dogfish, which is down in Delaware. So that's, you know, like a bunch of different places. So I don't want you to think that I'm just supporting one place. I mean, it is a local place, so support local business, of course. But yeah, the appropriateness of it, I wanted to make sure that I was addressing that. You know, it's like I'm equal opportunity when it comes to that stuff. All right, anyway. ref. I hit the wrong thing, cripes. The rough part is through this whole demonstration of me putting it in my calculator and all that stuff, you all have been done with this like for minutes now. I'm the slow poke. All right, so we have this. I'm gonna get a little lazy and do it this way. Just pop it in there. Oh, copy doesn't work. I have to save to. Oh, I guess I could just dump it on your phone. That'll work. Wait, where do I? What happened to my? Yeah, yeah. One for everyone. Wait, this is it, right? I just put it in the. Well, I didn't want to post it on my iCloud, but it's usually. Oh, I just hit done. That's why, and it'll ask me to save the photo. Okay, like I zigged when I should have zagged.
He was about to change his options.
It's like, get me out of here.
Yeah.
FYI, in case anybody's wondering, that part of this stuff doesn't show up in the videos ever. Not that it was like personal information or anything, but it's only what is being plugged into the this particular app. Oh, crooked. Come on, you son of a gun. There we go. Hugh Jackman. So we have, and again, so like I was saying before, like this is a vectorless solution. So we learned all about homogeneous vectors and all that stuff. It's like, yeah, you could write this as vector PMG, I think it was, is equal to vector this, that, and the other thing, but what does that tell anyone? Like if somebody wanted to know how much all this stuff costs and you showed them a vector with these values, they're not going to be thrilled, right? So what you want to do, they gave you the question in words, you're going to give the answer in words. So it's paper, you could go paper markers and glue sticks if you want, but unit cost unit price if you want. That all just depends on perspective. It's cost to one person's price to another. So paper, $1.75. Marker, an outrageous $3.60 for a single marker. You're out of your mind. Glue stick. All right, 95 cents, I can live with that. For a single sheet of paper, $1.75. Now, this is craft paper, so I don't know. It could be pretty fancy stuff. And if that's the case, maybe you do pay $1.75 for it. But it better be some piece of paper, I'll tell you that. Because even a dollar bill isn't worth $1.75. And that's a piece of paper, as you all know. All right.
That's the final answer.
That is your final answer, yeah. And again, what do we do? RF, write down our answer. But the structure of it is really the important thing. Now, admittedly, some other situations will be more complicated. I would not categorize number 2 as one of those situations. So I'm going to pop a star on that one for you. Hold on, let me just double check something. Yeah, number 3, number 3 is just straight up a repeat of number 2. Different numbers and stuff, but not really worth getting into. Number 4 is good, so you could pop a star on that one, but I would also understand if you're like, yeah, not going to do it because that one looks like conceptually a repeat of number 1, and it really is, but you know, you still haven't practiced one on your own, so it's not the worst idea in the world to try at least one where you're like, I know what I'm supposed to do. So I'll put it. Chemistry, nightmare. Physics, boom, I got you for that. All right, so, I mean, you want to talk like hydrostatic force, you want to talk electricity, I do it all right? So find the general flow pattern of the network shown in the figure. Now, a network, it could, you know, you think network, you think computer science and things like that, but a network is just talking about a flow into particular nodes, right? And so those nodes could be intersections of streets, all right? So if you're thinking about like, how do they determine when to make the light turn red and when to turn green, like what the intervals are? It's actually coming from concepts in linear algebra and graph theory and things like that, all right? It could be electrical currents, right? If you're talking about, like, for example, a 3-way switch, you know, if you're thinking about a situation where you have like 2 light switches that are going to a single fixture, like, how do you orchestrated so that the electricity is going in and out in the right order, right? These kind of situations really diagram that out. And in fact, if you ever looked at an electrical diagram, it's going to look an awful lot like this, all right? And in fact, we will do electrical diagrams before the course is over. So anyway, what we're going to do is we're just going to talk about equilibrium at these 3 points, the 3 nodes, A, B, and C, and just identify the direction. Directions going in and out of the node. All right, so at A, I can see that I have X coming into the node, X4 also coming in, and X2 is going out. All right, so the first decision you have to make is defining in and out. All right, so I'm going to let in be a positive direction. And out would then be a negative direction. All All right. Now, context is the driving force behind a lot of this stuff. So this is a contextless situation. But if I tell you that this is foot traffic, you know, like you're talking about, you know, pathways and foot traffic, maybe you wouldn't define in as being a positive thing. You might say, well, we're gaining all these people, it's going to be a crowd. That's a negative thing. You might call that the negative direction. But bottom line is, in or out, one is positive, one is negative, you take your pick. All right? So at A, what I'm getting is that we're going to be looking at it because it's an equilibrium, it's got to be a zero sum. I'm going to have x1 plus x4, I'll do my ins first, minus x2 is equal to 0. All right?
But it's like, you said x2 is
X2 is out, that's why it's a negative. All right, so I did my positives first and then my negative. I'll reorganize it in a minute. All right, so that's at node A.
And that doesn't violate whatever the line before saying, if you assume that the flows are all non-negative values?
Correct, because the flow itself will come out in the wash as either being positive or negative, and it'll work out. All right, and so B, we have x2 coming in now. All right, so that's a positive x2 based on my definition there. x3 is coming out, so minus x3. And then 100, that 100, it's not a variable, it's just a set quantity, but that's leaving node B. All right, so it's like if you're thinking about a theme park or something like that, and you have a courtyard or you have like a popular vendor or something like that, this is the flow of foot traffic coming in, coming out, but ultimately at the end of a certain period of time, you're gonna have 100 people leaving on this pathway, all right? And that's based off of data collection. But that 100 is in the out direction, so minus 100 equals 0. And then the last node is at C. So here you have 80 coming in, so it's a positive 80. You have x3 coming in, so plus x3. And then you have x4 going out, so minus x4, result is 0. All right, so I have 3 equations, but 4 variables. Now each equation doesn't contain all 4 variables, but 3 equations, 4 variables, which means one of them is going to be a free variable. All right, and that should have happened in the chemical equation one, but because I botched something early on, it didn't play out the way I wanted it to, you know, the correct way. Chemistry. So x1 minus x2, I'm going to put plus 0 x3 plus x4 is equal to 0. Then 0 x1 plus x2 minus x3 plus 0 x4, also 0. And then 0 x1 plus... I missed 100? Where's my 100? Ah, cripes. Equals 100. Because I'll just move that over to the other side. Just so I have all my variables together and all the numerical values together also. 0x2 plus x3 minus x4, and then on this side it'll be a negative 80. All right. So 1, negative 1, 0, 1, 0, 0, 1, negative 1, 0, 100, and then 0, 0, 1, negative 1, negative 80. And then we can pop this in. This is a 3 by 5. So 1, negative 1, 0, 1, 0, 0, 1, negative 1, 0, a hundo, and 0, 0, 1, negative 1, negative 80. Double check a Rooski here. All right, let's hit enter on that to make sure it's locked in. Good. And we get that. So I won't be lazy this time. I'll just write it in. 1. Oh, maybe I'll write it in, assuming it's going to let me write it in. Ref 1, 0, 0, 0, 20. 0, 1, 0, negative 1, 20. 0, 0, 1, negative 1, negative 80. All right, so that's my reduced form. But we do want to put it in the appropriate solution form. In my opinion, that is most conveniently the parametric form. All right, so we'd have x1 equals 20. x2 minus x4 is equal to 20. x3 minus x4, negative 80, which implies that x4 is my free variable. Let me get rid of that. So x1 still 20, x2 20 plus x4, x3 negative 80 plus x4, x4 is going to be x4, but we will have a condition on that, which I'll talk about in a sec. All right, and actually, let me make a slight adjustment here. Let me make that 0 plus x4. Cripes, come on. Oh, my pen just turned off. It's running out of battery, that's why. And so while I'm at it, I might as well take my x1 is just a solid numerical value. x1 is equal to 20, but I could still write it as x1 equals 20 plus 0 x4. All right, so x is going to be equal to 20, 20, negative 80, and 0, plus x4 times 0, 1, 1, 1. However, the condition, because of that whole non-negative thing, we want a non-negative flow. If every node is going to show a non-negative value, the condition is that x4 has to actually be greater than or equal to 80. Otherwise, x3 would be less than 0. fix that symbol. All right, so by the laws of linear algebra, x4 is a free variable, it could be anything, but by the context of the situation, because we're only looking for the activity in and out of the nodes to produce a non-negative value, it's telling me that I have to orchestrate this so that every instance, x1, 2, 3, and 4, will yield a non-negative value. In order for that to happen, x4 has to be 80 or more, right? If not, it would produce a negative value here, and so that node would be, well, if you really contextualize it, the net flow within that node would show a negative value, all right? So depending on what you define as negative, that could be a problem, all right? So if negative is inward, then that's saying that people are like still in the theme park after it's closed, all right? If it's in the outward direction, you're saying more people have left than were there to begin with, which doesn't make sense either, all right?
So the thing that tells us that it has to, x4 has to be greater than 80 is the fact that it's like a circuit, and a circuit can't have like a negative flow.
That, and, you know,
Oh, and also.
they don't also
okay.
said it
Yeah.
this one time, but the reason why it said it is because of what you said.
Okay.
Right.
Gotcha.
All right.